Now let's work through some examples from 3.5 rational functions. We've done the rest of it. We'll have done the rest of it in class. All right, so I've got just a few examples that allow us to kind of run through the situation. So vertical asymptotes and holes, they are really part of, or they're related to the idea of domain. And the domain has to do with the denominator. So the denominator would be 0 if x equaled 2. So the domain would be all reals except 2. X could be 2. All right, now at those places, at those trouble spots, the places that the numbers that cause your denominator to be 0, you're either going to have a vertical asymptote or a hole. To tell which it is, you need to see if it's possible to remove that factor that's associated with that number. So it would help for me to have that numerator factored. I can take out the common factor of 3. When I do, I have an x minus 1 left. So in factored form, r would look like that. And the x minus 2 isn't common up on top, so I can't remove it. I can't cancel it out. Therefore, that's a non-removable trouble spot. That's going to give us a vertical asymptote, and it's going to be the vertical line x equals 2. There are no other trouble spots, no other places where the function is undefined, so we don't have any holes. Okay. Now, for horizontal asymptotes, we can use that shortcut. We can consider the leading term on top. Think about the leading term on the bottom. Notice that the degree is the same. The polynomial on top and bottom have the same degree, right? So that's another thing. You can just look at how they have the same degree. So those x's, see how they could cancel out and you just have a 3 left. If it has the same degree, then you're going to have a horizontal asymptote equal to y equals the ratio of those coefficients. So y equals 3 over 1, which would be 3. But basically, it's looking at the leading terms and seeing what would happen when you simplify that, and then remembering that horizontal asymptote, that's really end behavior. So that's really what's happening to your function when you let x get bigger and bigger and bigger in the positive direction or in the negative direction. So if we did that, these are growing at the same rate, so we'd be approaching the horizontal line y equals 3. Now for x and y-intercepts, this is what you would do for any function. The y-intercepts are the easiest. For that one, you're just letting x equal 0 and working it out. So if you let x equal 0, you'd have 3 times 0 minus 3 over 0 minus 2. You'd get negative 3 over negative 2, or positive 3 halves. So the y-intercept would happen when x is 0, the y value would be 3 halves. If you are going to try to graph this, you might want to think about it as 1.5 or 1.5 so that you can see where it's located. Now for x-intercepts, you're looking for what would cause this original function to equal 0. That's going to happen when the numerator, a fraction is equal to 0. This over some number equals 0. Okay, some number over 0, that's undefined. That's the domain. That's why this happened. Okay, because 2 made the denominator 0. But when you're doing an x-intercept, you're trying to see what causes the function to equal 0. It's really letting the output, letting the y equal 0. So that becomes just 3x minus 3 equals 0, and then you work that out, and you get x equals 1. So you're going to have an x-intercept at 1, okay, and that's really going to be the ordered pair 1, 0. Now when you're reporting what an x-intercept is, it's acceptable to just say it's 1 or to say the ordered pair 1, 0. I like you to know it's an ordered pair so you can think better about where it would be if you were going to graph this. Okay. So I'd like to run through that idea on all of these so you get used to doing this kind of quickly. You're only going to have a couple where you have to go on and sketch the graph. So I'd like to just focus on getting that part done. So let's look at number 10. So it's going to help to have this factored. So I'm going to factor x squared plus x minus 2. So I'm x and an x. I'll use a 2 and a 1, and the 2 would need to be positive. Take the hint, a lot of times what you have, like in the other part, like in the numerator here, might be a factor you would see in the denominator. So that can sometimes help you. So the domain is where is the denominator 0. So you're focused on where is this equal to 0. So you can see x can't be a negative 2 and x can't be 1. So you have either a vertical asymptote or a hole, depending upon whether you can remove the factor associated with that number. Do you see how up here we have an x minus 1 on top and bottom as a factor? So this original problem could be simplified to just 1 over x plus 2. They're not exactly the same, but they're equal to one another everywhere except where x would equal 1. So you were able to remove the x minus 1 factor. So that means you're going to have a hole at the point 1 something. The x plus 2 factor you could not remove, and so that one's going to give you a vertical line that's going to be the vertical asymptote will happen at x equals negative 2. Okay, so the holes are the removable ones. The ones where you could knock out come from the removable discontinuities. The vertical asymptotes are the ones where you could not cross out the factor. They're non-removable. Okay. Now, we can get the y-coordinate of the hole, but notice if we plug the y-coordinate, the 1 in to the original function, it would have still had the x minus 1 there on the bottom, and so you would have gotten something undefined. So when you're trying to find the y-coordinate, you go to the simplified version, and you plug the 1 in there, and we find out that the y-coordinate would be 1/3. So that'll be the y-coordinate of the hole. And this would be the ordered pair right here where you would have a hole in the graph. Right? For horizontal asymptotes, we're just going to compare the leading term on top with the leading term on the bottom. Do you see how the degree is bigger on the bottom? So if I were to put if I simplified that, I'd still just have 1 over x. And if I have a 1 on top, but on the bottom, I have a number that's getting bigger and bigger and bigger, then that whole fraction right there is going to be approaching 0. So you'll have a horizontal asymptote at y equals 0. Bigger degree on the bottom, that's always going to happen. Okay. Now your x-intercepts, that's going to be when you're thinking about what causes this fraction here to equal 0. But you got to watch it on the ones with a hole because you're not going to have an x-intercept when x equals 1. I know it makes the numerator 0, but the problem is it also makes the denominator 0. So do you see when you look at the simplified version, you can't make that numerator 0 because it's a number, it's 1. So you're not going to have any x-intercepts because there's no way for you to take this and get it to equal 0 because that's not there's no variable up there. So you can't just turn it into a 0. Now for y-intercepts, you're just going to be plugging in 0. And you can use the simplified version when you do that. So let's put a 0 in for the x, and we get 1/2. So that means 1/2, or the ordered pair 0, 1/2, would be the y-intercept. Okay. All right, let's try another one. Here we have 3x over x squared minus 4. Let's get it factored and simplified. So x minus 2, x plus 2. and nothing cancels out. So the domain would be all reals except 2 and -2. And at each of those, you'll have either a vertical asymptote or a hole, so you have to think about what's happening here. We were unable to cancel out either of those. They were non-removable. So we're going to have a vertical asymptote at x equal 2, and we'll also have one at x equal -2. No holes, though, because the trouble spots did not cancel out. All right, now for horizontal asymptotes, we're going to look at 3x and x squared. And we notice if we were to simplify that, we'd still have that x in the denominator, and your horizontal asymptote is end behavior. If you let this number down here go towards either positive infinity or negative infinity, you're going to wind up having a fraction that is getting closer and closer and closer to 0. So bigger degree on the bottom, y equals 0 is your horizontal asymptote. For x-intercepts, would look at what causes 3x to equal 0, which would be 0. So 0 or the ordered pair 0, 0. And for y-intercepts, we'd plug in a 0 on top for x and also plug it in on the bottom, and we'd wind up with 0 for that as well, because 0 divided by -4 would equal 0. So the y-intercept is also the origin. Okay. All right, now let's do number 12. All right, so this one's already been all factored for us, and I also actually went ahead over here and did the long division. So that last thing I got by taking the x minus 1 and dividing it into this right here. You won't really need to do that for what we do in 112. All right, so looking at this, the domain would be all real numbers except 1. And then that x minus 1 factor was unable to be removed, so that means it's going to be a vertical asymptote at x equal 1. There are no other trouble spots, so we're not going to have a hole anywhere. Then when we look at x squared over x, the degree is bigger on top. That would be x over 1, or x. If we let infinity go in there for x, aren't we going to have an infinity, a really big number coming out? We're not going to have a horizontal asymptote. This graph's end behavior would be that it's going to go towards positive infinity when x is going towards positive infinity, and it's going to go to negative infinity when x is approaching negative infinity. So here you would just say horizontal asymptote, there's not one. It's really going to have a slant or an oblique one. And if we were asked to find it, this is what it's going to turn out to be. If we let an x go towards infinity on this, then this last term right here would be going to 0, and our original function would be approaching y equals x plus 2. You are not responsible for finding slant asymptotes in this class, okay, but I just wanted to complete that story. All right, so for x-intercepts, we're looking for what causes the numerator to be 0, so what causes x plus 3 times x minus 2 to equal 0. And that one's already factored, so you can tell when x equals -3 or when x equals 2. So you'll have 2 x-intercepts. Okay, and those are really the ordered pairs, -3, 0, and 2, 0. And your y-intercept is found by plugging 0 in. So when you plug it in and you do 0 squared plus 0 minus 6 on top, and then on the bottom, 0 minus 1, then you wind up with -6 over -1, which would equal 6. So the y-intercept is going to be at 6, or the ordered pair 0, 6. Okay.